Great. It's really great to see such a huge audience tonight on what is a very special night for the Edinburgh GeoSoc. Before we get into the main business of the evening, I'd just like to make one or two announcements. One of which is that the latest on that book you've all been waiting to buy, Geology of Scotland, the 5th edition, I think all but 3 chapters are through their final proof versions. I think there are 3 which are in early proof versions. And the last I hear is that the book is due in June. So have your credit cards ready. That's the latest I hear. And as proof, I can show you a chapter tonight. So it's getting there. It genuinely is getting there. The other thing to remind everyone is that we have another lecture next week. We're breaking our habit. Professor Rick Clough from Virginia Tech will be in the UK next week. It's his mid-semester break. And so he can get over from the States in his break in teaching. And he is very keen to come and talk to the Edinburgh GeoSoc. We've supported in the past some of his students in fieldwork. And Rick is the lead author for the Scandian chapter. Now, you've already heard from his co-author, Matthew Thirlwall, on the Caledonian magmatism. Rick has dealt with all the structural side of the Scandian story. So Rick will be here 7 o'clock next week to talk about the Scandian chapter in Geology of Scotland and all that pertains to that. So I think there's a brief comment from Angus on the Scottish Journal.
Thanks, everyone. You may remember this lovely publication that used to be available to all members. It's now online only, but we printed it. So exclusive deal, only £10. And of course, you were supposed to pre-order before Christmas to get your copy, but I've got some extra. So cash is accepted.
Of course you do. Hey. Don't all rush at once. Right. I think then we're in a position to get into the formal proceedings of the evening. Every year, the Edinburgh GeoSoc makes the award of the Clough Medal. And that is given to someone who has, through their career, made a major contribution to the understanding of Scottish geology, in effect. The full rubric is there on the Edinburgh GeoSoc web pages, but I'm not going to go into all those details. It's for someone who has made a major and outstanding contribution to Scottish geology. The nominations come in, and this year for us, it was actually a very easy decision for the committee to make. Tony Prave, who Tony was reminding me that we first met 2000, the year 2000, and our paths have crossed back and forwards on Scottish Dalradian geology in the main. We've never actually worked together as such, but I've followed Tony's work and his great range of geological research and work in all sorts of topics. And Tony has been based in Scotland for some 30 odd years. He blew me over tonight saying he's almost as old as I am. I had him as one of the young kids on the block sort of thing, but it turns out not. So he's much better preserved than I am. One of his nominators described Tony as a polymath, as a geological polymath. And that drew our attention. But when you look at his contributions in the fields of sedimentology, paleontology, metamorphic, igneous, and ore geology, there's not anything that he doesn't really turn his hand to in that sort of true tradition of Clough and the geology that he did. Driven, I suspect, by just unbridled curiosity and the need to know.
Jack of all trades, master of none.
Maybe so. However, we know that his work is all based on careful observation, on mapping, where the truth resides, in the rocks, in the field. And then with colleagues, all sorts of high-level techniques used to analyze those rocks, but to analyze those primary observations. So we've got this track record from the field to the publication. There are many, many publications and many, many citations of those publications, so that Tony's work in the Dalradian and on all of the other topics that he works on in a global sense is very highly respected, very highly regarded, and much quoted, much relied upon. So, and then there's all the teaching load and all the students that I know from St Andrews that he has inspired in the work that he does. So he more than fits all of the criteria to be awarded the Clough Medal. And so I'm going to hand over to our president, Mark Wilkinson, in a moment, just to actually hand over the medal. But right now, I'd like to personally congratulate Tony on the award, and it couldn't go to a better geologist. Thank you.
Well, thank you. Well, my part in this is limited pretty much to handing over this glorious silver medal and offering, of course, my personal congratulations as well. Thank you. Fantastic.
Yep. It's really only then to introduce Tony's lecture, Clough Medal lecture. I love the title. I'll leave Tony to introduce his talk through his title. Thank you.
Yeah, okay. Well, thanks. And thank all of you for coming. Yes, two titles that will be explained by the end of the talk. Okay. And before you go, and we've already hit technical difficulty. And I'll say what my next slide is while it comes up. I just want to acknowledge, and this is not going to be an Academy Award style thank you and thank my uncles and dogs and cats, but I want to acknowledge two people who have contributed and supported to my 28 years here in Scotland in terms of the research, and that's Tony Fellick and Rob Strachan, for their guidance, for their help, and not just for me, but really what they've contributed to Scottish geology and earth science in general internationally. And I also want to highlight three other people that I've had the privilege of working with over that time. Many of you will know Ed Stevens. He worked on Caledonian granites. But what most of you won't know is that if there is one person that you can point to who had the vision and the leadership to transform a department that 25 years ago was going to be closed down to what is now one of the finest earth and environmental science departments anywhere, it's Ed Stevens. So I just want to acknowledge that. And then these two characters sitting there, these are the unsung heroes of any science department. They are the technical staff. These are the people that underpin everything we do. They rarely get on a paper. They hardly ever write a grant, but they are absolutely key. And I'm going to ask for one-time audience participation because I know one of my colleagues is here, and I'd like especially the people from St. Andrews to thank them for the work. Okay, so on with the show. It's going to be of two parts. The first part's going to be a bit self-indulgent in a sense, in that it's going to be a journey down memory lane. And in part, it's because I need to at least talk a little bit about the stuff that I did that got me here standing in front of you today. And then I want to finish with something new. And the whole idea really is that, oh, that's a shame you can't see that. It's all right. The driving motive for me coming to Scotland in terms of Scottish geology was what contribution could Scotland's geology make for a deeper, more profound understanding of the key events, these moments in Earth history that were pivotal for changing the evolutionary trajectory of the Earth system. Good to go? Oh, there it is. Okay. Now that sounds like a grand question, but the reality, you do that and this doesn't work. There we go. It's up. It's up. It's up. Okay. Yeah, a grand question, but it's one that can be answered, because what we have to realize is 3 of the single most profound episodes in the evolution of the Earth's surface environments: the Great Oxidation Event around 2.3 billion years ago, the snowball Earth, these extreme climatic events between about 700 and 600 million years ago. And then out of those climatic extremes, what we can think of as, you know, Darwin's Cambrian explosion, the advent of animals, all of those are archived in the rocks that we call the highlands. So I am going to focus on that northern half of Scotland. There are the 3 major supergroups that we know. These are the sedimentary, metasedimentary packages: the Dalradian, the Moyne, the Torridonian. I have Moyne and Torridonian in brackets because just recently they have been reclassified into the Loch Ness and the Wester Ross supergroups. But Moyne and Torridonian are words that are embedded in our geological DNA, so I'm going to stick with those. Excuse me. And my interest was in how the rocks formed, not how they were deformed. And when I first arrived here, there were lots of debates about identifying D1, D2, D3, and if this 5-degree difference in the stretching lineation of the Moyne thrust had some deep, profound meaning or not. And that's great if you want to know about the deformation of structure. But I was interested in looking through those fabrics to see what was the paleogeography, what were the paleo environments. And I was told in no uncertain terms that the secret of the highlands is, if it's Proterozoic, that is the age during which those rocks were deposited and formed in the highlands, it's extensional. That is, it formed in rift basins and extensional basins. Now I'm going to plunge you into the deep end right away in terms of some Dalradian stratigraphy and some details, but we're going to extricate ourselves from that, and I'll explain what I want to refer to with this particular slide. I've highlighted the very first paper that I published on our journey in memory lane in terms of the Dalradian, this one of these major supergroups. It's the youngest of the supergroups that form the Scottish Highlands. And you can see the title. It was an alternative hypothesis published in 1999. There were 2 take-home messages that I want to highlight from this paper. There were a couple of things, but it was this: the Port Askaig tillite was 750 to 700 million years old, and that deposition occurred not in these extensional settings, but in these foreland basins or collisional settings. Now, the Port Askaig is probably the most iconic rock unit in Scotland. It's become one of the most iconic rocks units in the world because it does represent perhaps the finest example of a preserved ancient glacial deposit, which is these snowball earth rocks, and it happens to be one of the oldest ones. Welcome.
Thank you.
And a couple of years later, my colleagues and I, we extended this idea of thinking about the formation of the rocks and suggested that all of those supergroups that we talk about in terms of the highlands were initiated in terms of foreland basins, collisional orogenesis. Now, Graham, I just want to point out to you a little unconformity in the middle of Dalradian, and I'll come back to why that's significant based on some of the work that Graham and his colleagues have literally published yesterday. That was the response. This is bull poop. It was met with derision, those ideas. I was never able to get anything other than that first paper published. And part of that reason was that people thought that I was, as this quote says, giving not just a disregard to the work that had been done, but an Olympian disregard to the decades of scholarly research. Now, I wear this as a badge of honor because, I mean, this is almost poetry. And that was the first sentence of the first paper I tried to publish for a rejection. And I've carried that around with me as, like I said, a badge of honor. But what a difference a couple of decades makes. If you would have gone to the Bible of Scottish geology at the start of the century, the 4th edition of the Geology of Scotland, what you would have seen are those diagrams, that every rock unit in the Highland started its life, so to speak. It was initially deposited in a rift or extensional basin. At the top, I say 600 million years of extension. Now, this struck me as absolutely geodynamically improbable. There isn't a single bit of lithosphere on Earth of the scale of the Scottish Highlands, a couple hundred kilometers maximum across, of any time period that has experienced nothing, or for the most part, extensional tectonism. So this just didn't seem at all probable. Hence, this idea of an alternative hypothesis for the Dalradian extended into the Moyne and the Torridonian. And as I said, a couple of decades, and here we are now in 2022, and it's just been published, and it has been recognized that these rocks started out in terms of response to collisional orogenesis in the formation of foreland basins. Now you could say, well, this sounds like a bit of standard British navel gazing. You know, what's the significance? Well, the significance of that is that, as I show here, if you see the bit of the title, in terms of these grand ideas of plate tectonics, one of the grandest is that Earth's continental land masses at particular times form supercontinents. And here it is, the implications for models of supercontinental formation. And I've highlighted Scotland because Scotland has been central in thinking about particularly these North Atlantic cratons, these North Atlantic continents, how they have fit through time into these constructs as to ancient plate tectonics, ancient paleogeographies. And you say, okay, good, but those models are exactly what is then fed into thinking about how Earth's climatic systems, oceanic circulation, atmospheric circulation in the past has evolved over those particular land surfaces. So if you get the little bit of the jigsaw Scotland wrong, fitting into the bigger jigsaw of the supercontinents, and then plug them into these models, the whole thing sort of is a house of cards and collapses. So you want to get it right. And we think, at least at this point in time, we're a bit more correct than what we were 30 years ago. And that's a nice segue then for me talking about some of these ancient climatic models to launch into thinking about snowball Earth, the most climatic extremes, or the most extreme climates that the planet has really ever experienced. And the archetype, almost globally, for these ancient glaciations, as I said, is the Port Askaig. And the truism there was that it was 600 million years old. Now you say 100 million years, you know, when you're talking the Precambrian, what's the big deal? But again, the big deal is we need to get this right, because as you'll see, the timing of these glaciations is very vital for our thinking about biospheric evolution. The person pointing to this exposure of Port Askaig on Garvallic Islands, which is that big star, these are some small islands located off the coast of, just offshore of Oban, is Tony Spencer. He did his PhD 50, 60 years ago on the Port Askaig, and he is still driving one of the most dynamic, vibrant research groups into thinking about what these rocks represent for our understanding of deep time climate change. Excuse me. And the other stars are just some of the key localities throughout the Dalradian where these rocks are preserved and exposed. As I said, turn of the century, it was ignoring decades of scholarly research. Now, the Port Askaig is being offered up as the place on Earth that you would want to go for a global stratotype and section point for studying this time in Earth's past of these ancient climatic episodes in terms of snowball Earth. So I want to push back time a bit here, because basically I've started you at memory lane. We've ended at memory lane. Now I just want to kind of fill that in on a journey down that bit of memory lane as to how we got to where we are today. If we look at the grand scale of Earth system evolution through time, and what you see in the top graph is a very simplified trend of carbon isotopes. They're on the x-axis, and we see time on, on the y-axis, we see time on the x-axis starting from the present on the left up to about 3.5 billion years ago on the right. And that envelope captures the variation of carbon isotope values at those particular time intervals. And you can see that there are two major perturbations of that trend. in a way, you can think of carbon isotopes as a proxy for the efficacy of how the biosphere is functioning. And if we see perturbations in the carbon isotope signal, the implication is there's some sort of perturbation in terms of what's happening to the biosphere. And the Proterozoic time interval is bookmarked by these two extreme perturbations. The Neoproterozoic, also coincident with these climatic episodes of snowball Earth, and then the Paleoproterozoic with what is the Great Oxidation and Loma Gundia-Thule events. And I'll let those rest for a minute, and we'll start talking about particularly this time interval, which has garnered a lot of interest over the last couple of decades. It's like what this artist's rendition is showing, this concept that you've had a glaciation so extreme that ice existed from the poles to the equator. Two time periods that have been documented so far, the younger one, the Marinoan, the older one, the Sturtian. As you can see from the range, these are over millions to tens of millions of years. These defy understanding in terms of what we think we know about climate today, all right? There was a third glaciation, this gas gears, it's a bit younger at 580 million years. So you had these three climatic events that had that postmarked this period in Earth system evolution, right around the end of the Neoproterozoic. Now, associated with those, as I said, was this idea of these carbon isotope excursions. And this is a blow-up view of that diagram I showed you previously. Time now is on the X going from about 900 million years ago to about 550 million years ago, the time of the base of the Phanerozoic. Y-axis is values of carbon isotopes, and this has been called the bumpy ride, okay, because of these extreme amplitude shifts. And this is a nice diagram because on the extreme left, I got this pointer, you can see what we know from modern day carbonate platforms and shelves in terms of their overall isotopic values, and then what you can see from the Cenozoic deep sea. So these are extreme perturbations in terms of carbon isotopes. They're associated with, as you can see, those glacial epochs, the Sturtian, Marinoan, and gas gears. And I've also circled and highlighted a particular unit known as a cap carbonate. These are associated with the aftermath of these snowball Earth glaciations. And the little inset map shows you that these have been documented worldwide. And there are a hell of a lot more places than what's shown on that map, and to where you can see these trends in terms of carbon isotope space. And last but not least, with respect to this particular time interval, this Neoproterozoic, that's what the most complicated, complex form of life looked like for 3 billion years on our planet. We hit snowball Earth, these climatic extremes. The idea is they created environmental bottlenecks, and once climate ameliorated, you start getting every extant life form that we currently have on the planet today, coming right down to basically us, okay? So there is this wonderful aspect of the Scottish rocks in our back garden, an archive of extreme climate events that the world has never seen before or after, extreme carbon isotope events, and basically a potential link to us, biospheric evolution. And this was great. You know, I was like this little infant there, giddy with excitement, you know, thinking, you know, people really buy into this, wrote a big grant proposal, submitted it to the research councils, and that was the response. Nothing left to learn from this scrap of Northwest Europe, hence the title of my talk. This was in 2000 or 2001. I never got a grant funded from the research councils to work in Scotland. But what I was lucky enough was to work with colleagues like Tony Fellick and Rob Strachan, where we were able to scrape a few shekels together to do some field work, run some analyses, and continue with the work that I'll show you in a moment. But coming back to this particular comment, there's really only one appropriate response for something that is pig ignorant and as small-minded as that, and it's that. And I did say that to the face of the person that made this comment, and I suppose in part that's probably why I never did get a grant funded. I've already talked about the Port Askaig, right? This is an in-your-face glacial deposit. Ancient glacial deposit. But like so much of Earth history, you have to go where the archive best records the best episodes of that historical time period. And you have to shift from Scotland for a moment to go to Namibia, which has one of the finest records of the younger snowball Earth glaciation, the Maranoan. And this is a nice photograph showing you that glacial diamictite, the melt-back deposit of the snowball Earth with these beautiful drop stones and ice-rafted debris. And then I'm highlighting just above my colleague Dan Condon's fingertips, the cap carbonate. And this is then this glacial cap carbonate couplet that define these snowball Earth episodes worldwide. And they can be pretty magnificent. This is the Maranoan glacial cap carbonate couplet in Namibia. And the point is that I want to make from this slide is not to show you a pretty picture and to say, oh, look how many places I've been on Earth. It's that these types of deposits in this kind of magnificence occurs on things like continental platforms, continental margins, continental shelves. So if you really want to see what happens in deeper parts of the basin, you have to migrate off of the continental shelves down into the basins. And this is what you see. That sorry looking folded brown marble is the entirety of the cap carbonate sequence. You can see this pen circled. It's a marker pen for scale. This will make my boss, my head of school, happy. These are at sillimanite grade. Interestingly, it retains its carbon isotopic signature, so you know you're looking at a cap. But most importantly is that as you move around through the central zone of Namibia and these deformed rocks, what you can find are these drop stones, lone stones, like on the left, and you see the hammer circle for scale, and this ice-rafted debris. And unfortunately, this bar is hiding a coin, which is about the size of a pound coin. So that little pebble in the center is about the size of my fist. Now, the time of deposition for the rocks in Scotland that were occurring at the time of the Maranoan glaciation were also being deposited in a deeper part of the basin. So you don't look for the Port Ascaig's Tau glacial unit. You don't look for a cap carbonate like we see in the Maranoan. What you look for are equivalents, and this is the little brown limestone, okay, of Barrow. And there is an equivalent deep basinal cap carbonate here in Scotland. Underneath it, when you walk around sitting, it caps these lone stones, drop stones, and this ice-rafted debris. And as I said, there was a third glacial. And in that third glacial, we know we've had this in Scotland for some time, but if we look into the framework of Neoproterozoic Earth history, we can start tying these physical stratigraphic frameworks together. And this is the Macduff and Loch Nakill boulder beds, and again, with some beautiful drop stones. They don't have to be big. You know, size doesn't matter when it comes to these kind of aspects. You just need to see the in further process response. And so this idea of matching a physical stratigraphy of glacial deposits, you want to try and match that then with the carbon isotope chemostratigraphy. So you have two, what you could think of more or less as independent data sets. And luckily enough, and in the room, St. Andrews always has good students. And this is the work of Gillian Mackay I'm going to show you. She works here in Edinburgh now. And she was central in tying the Scottish mainland to the north of Ireland Dalradian. And just to show you how reproducible these particular excursions are, this is the Cranford limestone that Gillian worked on. Tony's lab produced the data. The exposure isn't quite as good as it is in Namibia, but nevertheless, as you go along the shoreline there of Mulroy Bay, you can pick up that stratigraphy. And what I'm just going to superimpose on it is that cliff that you see from Namibia. All right. You know, it's not one-to-one, but the expression is there, the amplitude is there, the trend is there. And so this allowed us then to do this right across Scotland. And this is what you see over a decade worth of work. Our Shekels put together and published this and got the data right across Scotland, Ireland, and Shetland. And therefore, in the next version of the Bible that will come out, Graham tells me in June, and I heard of what year, which is probably a very good comment. What you will see is this particular diagram in which we are now trying to tie together all of this information that has been synthesized, summarized over 20 years worth of work in which you have not just one, not just two, but several different data sets that are independent of one another to allow you to build this framework of a physical stratigraphy, the three glacials, carbon and strontium isotope trends. Ian Fairchild and his group have been central in developing a strontium isotope curve for these rocks. The data are reproducible right across the British Irish Isles, and most importantly, they are compatible with worldwide trends. And significantly, it does all snuggle quite nicely within what we do have is the few paltry age constraints for these rocks. And I showed you an unconformity at the beginning I had circled, and what I just want to say is that this story is not over because Graham Leslie and his co-workers have, over many decades and some painstaking mapping, recognized what I was fantasizing about in 1999. They've actually documented it as a major unconformity sitting in the middle of the Dalradian. And so watch this space in terms of how this story evolves. But what we can do is we can nicely tick that box and begin to answer, at least partially, this question of, can we use Scotland's geology to say something interesting about these events that shaped Earth system evolution? And in this case, yes, we can, all right? But what about the Great Oxidation event and the Lomogundi Yatuli event? The Lomogundi Yatuli event is the term given to this huge perturbation of positive carbon isotopes. The name comes from the Lomogundi region in Zimbabwe, where the rocks were first identified, and the Yatuli region in Karelia, which was part of Finland, is now part of Northwest Russia. The Great Oxidation event is, of course, that time in Earth history when free oxygen, that free dioxygen molecule was first started to make abundance in the Earth's atmosphere. And make no mistake, other than the origin of life itself, the Great Oxidation and Lomogundi events were probably two of the most pivotal episodes in the history of life on this planet. Excuse me. All right. So it's important to try and understand the drivers and the mechanisms that drove this. And here is a data set. Sorry, here are a compilation of data in two graphs. And let me explain these. And I apologize because on this one, the time goes in the opposite direction. Present day on the right to about 4 billion years ago on the left. And just focus on the bottom one for a moment. This is the guesstimated trend in terms of atmospheric oxygen composition. Next to nothing in the atmosphere for the first 2.5, 3 billion years. And then this very sharp rise at around 2.3 billion years ago, the Great Oxidation event. It levels off, and then there's another rise about 500 or 600 million years ago that Rachel Wood, who's sitting in this audience here at Edinburgh, has been central in documenting. And this has taken us up to our present day level of about 21% or so oxygen. Superimposed above that on the same time scale is that same carbon isotope curve. Just focus on the dark envelope, the black envelope. We're not going to talk about the Cap Delta 33 data. This is a talk all in itself, but what I want to highlight is this Lomogundi Yatuli event. And what you're talking about in terms of carbon isotope space are values on the order of 5, 10, 15, even 20 per mil. These are values that are extreme in terms of carbon isotopes. The world's oceans today, on average, are about 4 plus or minus 4 per mil. What has intrigued, what has consumed, what has excited the international earth science community about these two data sets is what appears to be this temporal coincidence. Temporal in the sense of the Precambrian, we're spanning a couple 100 million years. But what it has led to is what has become the consensus model, and I'm going to use a slightly derogatory term, groupthink here, in which for the last couple of decades, entire careers have been built on documenting what appears to be this global, coeval, and hence interconnected aspect between these two events. And tens upon tens of science, nature, etc. papers have been published to document this, culminating in what you can see there, what is considered the redox history of Earth. And to be accurate and precise, this really should be the redox history of Earth's surface. Okay? What does Scotland have to say about that? We are lucky to have one very small patch of Paleoproterozoic rock in Scotland. It's called the Loch Maree Group. I've highlighted in the box where it occurs. You're looking, this view is to the northeast. Those of you with sharp eyes could see the town of Gairloch in the distance. And a seminal paper was published, Tony Fellick and Andy Baker, and I actually looked 35 years, 1 month, and 2 days to the day this paper was published. And what they documented was the existence of the preservation of positive carbon isotopes, positive carbonate-carbon isotopes, and what it says they're 2,000 million-year-old seawater, and in rocks that are basically at amphibolite facies. Now, I'll just change that Lewisian into Loch Maree Group because that is the rocks. And what they did was what every good isotope geochemist does, make a cross plot between carbon and oxygen to see if there's trends or connections. I'm not an isotope geochemist by any stretch, but I am a stratigrapher. And so I was interested in what their spatial pattern was. So I just got curious and I plotted it on a map. And what you can see is that they're separate. They don't plot together. There's not a mix. They form a trend and they're separate. And if you put this on what is an embarrassingly simple geological map of the Loch Maree Group, what you see is that this Loch Maree Group is a synform. I think it's well, I'm convinced it's a syncline. And what you have are the occurrence of the Loma-Gundy-Utuli values, these highly positive values, occurring in 2 belts of marbles that exist adjacent to the Lewisian boundary of this folded metasedimentary package. And through the core of that syncline or synform are the quote unquote normal values. And right at the bottom, and you can't see it, I have drawn scoury dikes. These are these thin little black lines that are cutting the Lewisian gneiss, but are truncated at the base of the Loch Maree. Therefore, the Loch Maree is younger than the scoury dikes. And we can look at this pattern of isotopic expression in terms of the distributions. And I'm just going to label these belts A, B, and C. We're going to make a little stratigraphic column. This is work that Graham Park and others have done over many years. And I'm highlighting here on this the age constraints you have. There is an intrusive rock, this Ards granitic gneiss, that's been dated around 1900 million years. And at the top, the age constraints come from what are detrital zircons that Martin Whitehouse got in the turn of the last century at 2.0 billion years ago. And I thought we should try and tighten that a bit. And so I had a student work on the scoury dikes and this unpronounceable, at least with my accent and tongue, Gallic name, 1989 million years. So it tightened it. Not a lot, but enough, because if we then look at the pattern of these rocks in terms of their stratigraphy, their physical stratigraphy, their isotope data in terms of the carbon isotopes, what we were able to do with the dike and the existing intrusive age is to bracket that excursion, these heavy values, and you can see they're up to +10 or +15, so they fit the definition of Loma-Gundy-Utuli. So here's the groupthink model. Global, coeval, interconnected. The Loch Maree rocks are 100 million years younger. So this led us to say, well, certainly they're not coeval if we accept our data, and it led to question marks about global or interconnected. The same response from the International Earth Science Committee this time. We couldn't get this published anywhere, right? Nothing. So what do? You do what everybody does, you dust yourself off and you say, okay, we're going to show the naysayers that we know what we're talking about. So what I did, about 15,000 carbonate-carbon isotope data that are appropriate for the time interval and for trying to use as analogs for those types of rocks, focused on gathering data for the Loma-Gundy-Utuli interval that was at least had enough descriptive sedimentology that we could then place them into these 3 very, very broad paleoenvironmental categories, essentially going from shallow to deep: coastal shoreline, often evaporitic, nearshore marine, and open deeper marine. And that's the data set for 2 billion years of Earth history, going from 1 billion years ago to 3 billion years ago on the left, carbon isotope values on the y-axis. I have highlighted what people, not us, what others defined as the Lomagundi-Yatuli event. There's a histogram of the data shown there. And let me put the data with what we see as the groupthink model and the trend in carbon isotopes globally. And this is one of those proverbial Damascus moments, you know, the light bulb goes off above your head or the penny drops. I showed this to my colleague, Eva Stukin, and she saw within a second what it took me about a day to see, and what I would hope all of you would see, because the question you have to ask, where are the normal values in this so-called Earth system model of carbon isotope trends? Now, we can think about why those data aren't there. Try and answer that. But I want to stress that because, you know, sometimes you have to reinvent the wheel, or at least what you want to do if you're going to reinvent the wheel, make it a better wheel. These are the data that were published in 1975, some of the first data sets from the Lomagundi region. Those workers said, this is not a global perturbation, it's local, all right? The reason they said that is because they did not ignore their so-called normal values. They could see in their data that this perturbation was associated with values that weren't perturbed. Just to show you that there are some rocks that we looked at, this is the type of data that we use to categorize our paleoenvironmental interpretations. These are cores that you're looking at. Most of these rocks have to be used from cores because 2 billion, 2.5 billion year old rocks, a lot of shit has happened to them. You need to get fresh samples, not stuff that's been weathered. And on the left is some examples. This is a beautiful example on the far left. The very bottom, this is salt, that pinkish reddish color. This is exactly the stuff you put on in your steak when you eat it. And what's lovely about that particular exposure is if you look at those thin layers of mud, sorry, I have a pointer, you can see these desiccation cracks that are cutting this mud layer. So you know this was exposed at the surface. And you actually see the mud is gray and black, but the desiccation cracks in the overlying mud is red. These are the first red beds on Earth. This is when you're seeing Earth's atmosphere being oxygenated. On the right is just a beautiful example of pseudomorphs of calcium sulfate nodules, gypsum nodules. And on the right, I just have an image I clipped off the internet to show you that, yes, these things look similar in the modern and the recent. And for the more open, deep and marine, we use the classic kind of sedimentology, cross-bedded, rippled calcarenites, these beautifully laminated rhythmites, and those are the real colors. Those are just showing redox fronts. And this is an image on the left of, again, just clipped off the internet. It's offshore Greenland, similar type of thing in terms of seeing these offshore shelf, deeper marine, open marine deposits. So this is what our data looks like if you plot it as a histogram, and when you separate the data out in terms of the paleoenvironmental setting. These are the mean values, 8, 6, and 1, as you go from shallow to deep. But most importantly, if you put that then on a trend through Earth history, and again, I'm switching the x-axis around, 3 billion years or so ago on the left, today on the right. And the beauty of this diagram, which we finally did get published 1.5 years, 2 years ago, is that everybody asked the wrong question. Everybody focused on the wrong data set, because the real story of the carbon isotope trend is this. For 3 billion years, the oceans were not majorly perturbed. So the original workers were right. Those excursions that everybody wants to focus on to get that sexy science Nature paper, these were local phenomena. If you want to talk about how the world functions, you want to go to where the major mass reservoirs are, all right? So the punchline to that paper that got published in the Journal of the Geological Society of London, thanks to some enlightened editors like Graham Shields, it's a facies phenomenon. It's unique to Paleoproterozoic coastal shoreline settings. And what it represents is the lateral gradients and carbon isotopic compositions of contemporaneous water masses, what we see in the modern. What a difference then breaking free of groupthink makes, because all of a sudden now, we have to deconstruct these ideas. And the punchline here is simply that if you're going to understand Earth's oxygenation, and if you're going to understand biogeochemical cycles of which carbon isotopes are central, then we have to understand what drove this particular excursion. And it's all as a consequence of a little package of rocks called the Loch Maree group here in Scotland. Hence that question about, can Scotland's geology answer big questions? Absolutely. So you're only as good, they say, as what you did last week. So that's all old news, right? So now I want to finish with something new. And we're going to talk about life. Not train spotting, but this. It's been known for some time that some of the rocks in the Highlands, and we're going to shift to the Torridonian, had fossils in them. These fossils are fairly simple eukaryotic cells, like you see up there. I clipped this from Preston Cloud's paper. And this has been known for 150 years. This is what I talk about it in the Northwest Highlands memoir, 1907. A number of people, including myself, have published on features that give us evidence for life on land. And this is just a microbial mat, or evidence of a microbial mat with a pound coin for scale. But the real breakthrough came from the work of Paul Struther and Charlie Wellman, where they were able to recover these exquisitely preserved eukaryotic fossils from the Torridonian, the Diabeg Formation. And as you can see, I've highlighted non-marine. And the message from this particular paper is that these assemblages indicate eukaryotic evolution on land commenced far earlier than previously thought. So this is a major aspect of thinking about biospheric evolution, coming again from Scottish rocks. The significance of the idea of non-marine is that if you look at the trend of life through the Proterozoic, all of those localities indicating these different magnitudes of genera that are preserved, only 2 are interpreted to have a non-marine biota. The others are marine. Come from the Diabeg rocks. They, in the blow-up map on the left, all those little dark squiggles are the outcrop patterns. And I want to highlight this because some of the outcrop patterns are a consequence of, erosion, discontinuous nature of the outcrops is a consequence of modern erosion. But a lot of them are actually reflecting an older paleogeographic signal or fingerprint. And the reason I can say that, there's the Diabeg on the left. It's these gray, dark gray colored shells and sandstones. And where they are preserved is typically in these lows of paleo valleys. Now, unfortunately, this one, there isn't any Diabeg preserved, but I just want to give you the image, because what you are looking at is a 300-meter relief paleo valley. Some people would say this is the oldest preserved landscape on Earth. This is not due to modern glaciation. This was prior to the billion-year-old deposition of the Torridonian sandstone, all right? So we're looking at these paleo valleys that get infilled by these dark gray shells and sandstones. Now, I want to drive home this point. And I wanted to do this, and I know these figures are fairly awful, but I wanted to make sure that I'm not trying to convince you of my argument versus what was said by the original workers. So I've just literally gone in and cut and copied sentences out of these papers. 1979, Sandy Stewart, who is the doyen of the Torridonian, spent his whole career working there, published a paper in which he talks about these initial interpretations of those units being, you can see I've highlighted marine tidal, but as is typical for people wanting to think about sedimentological evidence, it's ambiguous, okay? So what do you do when you have ambiguous sedimentological data? You do what everybody does. You turn to your geochemistry colleagues and say, is there a geochemical proxy we can use? And at that time, one of the best geochemical proxies to try and determine salinity, or so they thought, was the boron content of shells. And what they did was separate small illites, 1 micron in size. The bottom line is they say they're non-marine. And so if I just do this, and when they say non-marine, and again, this bar is cut it off, think lake. They want to make them lacustrine. Now, whenever I read a geochemistry paper, it says a value about. A red light goes off in my head, and the antennae twitch. So I just plotted their data on a very simple graph. Boron content, values go from about 70 to 180, and what you see there are the dots of their boron content for the different samples that they had. So you say, how good is this proxy? You go to look at what other people have used of this proxy. So you go through the literature, and there are a lot of papers, but I picked this one particularly because it's looking at a unit that is about the same age of the Diabeg. I've underlined where the workers have said the geology is consistent, there's no ambiguity, and I've just highlighted in red the values that they use based on their geological interpretation of the boron content for these values of the rocks. And if I put their bounds on the data that was used, and it's the only data set that says that the diabase is lacustrine, there's nothing else, we come up with some ambiguous geochemical data. So let's avoid the ambiguous and try and go right to the unambiguous in the diabase. And we're going to first start with the kind of thing I do is I'll look at the rock. On the left is herringbone cross strata in the diabase. What's herringbone cross strata, you say? Well, let's go to our Wikipedia Bible. Herringbone cross stratification, a type of sedimentary structure formed in tidal areas, right back to the original interpretation where the current periodically flows in reversing directions. I clipped that figure off of the Wikipedia page. And those of you with sharp eyes, you'll see it's inverted because I had to invert it because it's eerily similar in scale and character to the diabase. And I wanted to show the force that's migrating in the same direction. You don't have to look in coarse sands. You can look in fine sands and silts, okay? You can see the pen tip for scale. It's the same scale for both. And I'm just going to flick back and forth. I've made some sketches of the cross-bedding of these very small lenticular ripple and pinstripe ripple sets, which show bimodal flows and reactivation surfaces. I'll let you get your eye tuned in. The slide on the right has one of these very early phosphatic diagenetic nodules within which some of the fossils have been recovered. And so those early phosphatic nodules were being deposited in a setting, at least soon after a setting that was influenced by tides and hence a marine setting. And there are other features. We can look for M2, M1 tidal indicators in terms of things like tidal rhythmites and tidal bundles. The images on the left of those two sets of figures are the diabase formation. And again, I just went in and clipped some images off the internet in which the interpretations based on modern rocks and fossils allow you to infer tidal settings, okay? So I'm lucky enough to work with a very good geochemistry colleague, Ava Stukin, and we've had a student, Grace Nelson, who is, together with Ava, produced what you could call unambiguous geochemical data sets for these rocks. They took them apart. They looked at a whole array of different elemental ratios that are used today to try and determine salinities, and this is just some of the data set. And the punchline is that their data suggest mostly oxygenated, fresh to brackish waters. So it seems like we're in this contradiction at the end, right? A good solid geochemical data set, not this kind of iffy boron content in shells data set, and a good sedimentological data set. And so the question is, what can satisfy these what seem to be contradictory data? Because it has to be either lacustrine or it has to be marine. Well, it doesn't, because us living in Britain, we have the answer sitting at our doorstep, and particularly me, I can look out my bedroom window and see the Tay estuary, all right? So we thought, this is great. Let's put together a paper. It got a bit of a kicking, not as much as my usual manuscripts get, because we thought, my God, you know, this is a significant finding. We're talking about this idea of a biospheric evolution of eukaryotic life on land. And what's bigger than that? Well, these were the comments, and I'm putting these up not to be self-satisfied, but I want to show the issue that you deal with in geology today when you're thinking about sedimentology and trying to convince people of process, okay? These are the comments. You can read them, okay? You know, I remain unconvinced because the BGA values, the boron over gallium, say freshwater, even though there's lots of evidence for tides. Tidal features can develop in lake environments. Now, this makes my teeth grind. And I'll show you why, okay? And Ava, my colleague, says you got to do something more than moan about this. And then this manuscript should be sent to a sedimentologist. Ouch. But double ouch, because it should be a Cambridge sedimentologist. One more reason why Scotland should go independent, I suppose. And what it comes down to is this. You know, field data is often viewed as being descriptive, subjective, you know, not very rigorous, collected by people who walk around dragging their knuckles on the ground. And of course, you know, we have the opposite view of where you get data that's analytical, rigorous, quantitative, it has deep meaning. And, you know, and this is highlighted by two quotes that I really like to always bring to people's attention. One made more than a decade ago by Bruce Watson, which is still true. This ability to measure chemical signatures has far outstripped our ability to interpret those signatures uniquely. And that's fair enough. That's with any data set. The bottom one, though, focuses specifically on the Proterozoic. And it says that, you know, we have a problem and critical reevaluations of data sets are going to be needed to solve that problem. It's not the data that are generated, it's the context within which those data are interpreted. And that's what I want to do in terms of finishing up. As a poor wee Scottish sedimentologist, unlike our clever Cambridge colleagues, the very first lecture that I give to students in my third-year sedimentology class, I start with this as one of two photos. And I ask them to interpret that image. And I think most of you would look at that and say, well, it's straight crested ripples. They look symmetric. So wave ripples, you know, some shallow marine setting. Well, you see, you don't have context, because as soon as you put it in context, these are ripples that formed in the mid-ocean ridge in the North Atlantic. And they're easily explained as a consequence of Helmholtz waves that will form at the interface between two density fluids moving at different velocities. And this is what you had there, two different density fluids in terms of temperature. It's the same kind of thing you see with the atmosphere in terms of clouds, okay? So let's take this apart, right? There's the tidal estuary. This was work done by my colleague, John McManus. He spent his career, he's now retired, studying the Tay estuary. And I'm just showing you two data sets for what is a tidal cycle of salinity measurements. If you're 10 kilometers inland, you can go from brackish to purely marine. If you go another 10 kilometers into the estuary, you're basically looking at fresh to brackish. And I went this morning onto tides for fishing to look at tides at the mouth of the estuary or at Perth, 2 to 3 meter high tides. So there is absolutely no problem interpreting two data sets which are seemingly giving you different answers if you understand the context and the environmental setting and the processes within which those data sets can be generated. Now, what about this, okay? Yeah, tides do have lakes, but they're bloody tiny. You know, we all know the inverse square relationship between two masses attracting one another. You need a lot of mass to generate a tidal response. 5 centimeters, the largest lake on Earth today, aerially, the largest by volume lake, Baikal, 2 centimeters. And flipping hell, how do I get rid of this? Okay, it doesn't matter. It doesn't matter. I'll tell you what the answer is. The bottom relationship is, it's just a simple empirically derived relationship in which you're looking at viscosity linked to a geometries of enclosed or confined bodies of water with respect to the tidal amplitude, how much that would generate then what you see Umax, which is a maximum shear velocity. The answer, if I use the most extreme values for Lake Superior, is 8 centimeters per second. Let's look at the Tay, all right? The Tay, we can do a little simpler way of thinking about deriving flow velocities, and I'll show you why I want to do this. We can just look at the discharge relationship. Discharge is equal to cross-section area times velocity. We come up with these types of numbers. The second week of my 4-week sedimentological teaching in Scotland, we cover what are known as bedform stability diagrams. And these have been generated by engineers and physical sedimentologists and hydrodynamicists for years to try and link textural relationships of sediments, erodible substrates with flow parameters, things like flow velocity, flow depth, shear velocity, Reynolds numbers. In this case, we're just looking at flow velocities. So let's just put those examples that I showed you more or less in a proper place from the diabase formation. The silt, very fine sand, small ripples, the coarse sand, medium sand, or the herringbone. And let's show you what lakes and tides do. Okay. So yeah, you have tides and lakes. They do bugger all in terms of sediment transport. Okay. So, you know, luckily, we have a happy ending to that story, in spite of those comments, in that just last month, Grace's paper got published. And I want to finish with the closing line of that particular abstract. The Torridonian may be representative of the low salinity habitats predicted for ancestral eukaryotes, estuarine settings with gradients in water chemistry, may have facilitated the transition of eukaryotic life from land to sea. Now, I don't know of how many studies that can have more of a profound, deep potential impact for understanding how life and Earth have co-evolved than something like this coming from Scottish rocks. So, Secret of the Highlands, the first quote, it's not necessarily extensional, it's complicated. My attempt wasn't a disregard of centuries of research or decades of research. It was just simply a different way of looking at things. And that different way of looking at things wasn't really liked initially. And this very small-minded, ignorant comment, what I'd like to say to that person even today is that there's much left to learn from this scrap of Northwest Europe. And I said I promised you 4 quotes. Neil Young, who's probably the finest singer-songwriter of his generation or any, he had a very tempestuous and tumultuous relationship with his band and with the music industry. And when he was asked about this, I've always liked this quote. It's always been about the music. Nothing else mattered, not commercial success nor personal feelings. And what I'd like to do is finish where I started and to thank my colleagues, particularly Tony Fellick, for allowing me to have a very stubborn view similar to that, where it's always been about the rocks. It's not about the success of proposals or for getting publications out. And I said there were 2 lessons, and I suppose my 28 years here in Scotland, the Royal Society says it all, right? Take nobody's word for it. And the best one is keep calm and stay open-minded. Thanks.